Okay, everybody, how's it going? This is Rob. I'm the teaching assistant for Analysis and Representation 2 at the University of Massachusetts in Amherst. We're going to go through a tutorial of the waffling definition in Grasshopper today. So the basic concept is to create a series of interlocking ribs that will represent complex surfaces. So we're going to do that using Grasshopper, parametric modeling tool for Rhino. You should be pretty comfortable in Rhinoceros before beginning this tutorial. This is a fairly advanced one. Okay, so as we've been doing in class, we're just going to go ahead and set up sort of the concept and a diagram of the definition, and then we're going to go from there and start to figure out what the different steps are. So first, we're going to look at the final desired output, which is to section any solid into interlocking ribs, and then get the line work ready to be cut on a laser cutter. So the ultimate output here is a three-dimensional physical object. The input parameters are going to be the original solid, so any solid that we enter into the definition. The variables are going to be the rib spacing in the x direction, the rib spacing in the y direction, and the rib thickness. There are certainly a lot of potential changes that you could make to the definition to make those values more interesting and less consistently spaced, but we're not going to go through those. So in terms of an approach, we're going to first create vertical planes at regular intervals that are all going to be intersecting with the object. We're going to get rid of the ones on the outsides, so we'll just have the interior planes. So we'll do that first by creating, from our starting object, we'll go ahead and create a grid on the lower end of a bounding box of the object so that it'll fit perfectly. We're going to do that by taking the lines around the bottom surface of the bounding box and dividing those into a given number of segments, taking those points and creating lines across to create a grid. Then we are going to turn those then we're going to turn those lines into planes, and that's going to look like this. So it's a grid of planes, a three-dimensional grid, and as you can see, those are intersecting, so we're going to go through and we're going to find the intersections between those planes and the object. So that's going to look like that. Then we're going to create a series of solid ribs based on those lines, but those are going to be first we're going to take the original curves and turn those into planes, and then from there we'll extrude those outwards. First we're going to move them over half the distance of the thickness and then extrude them back the full thickness to get solid ribs, but those are going to need notches, so that's the next step. So we're to create the notches. Most of the definitions for creating waffles use a different system. You'll find a lot of them online. I think this one's better. This is from Victor Lung on the Grasshopper forum. This is a really brilliant script. A really brilliant definition, and it seems to work a lot better under a lot more with a lot more objects. So we're going to go ahead and use it. So essentially, what we're going to do is find the intersections between the ribs, which are going to be curves here. So that's a brep intersection. So that'll give us curves, and then we're going to take those curves and we're going to create narrow vertical boxes, which Victor has called French fries, around these intersections. So that's going to look like this. So these boxes, we're essentially going to subtract, we're going to move them vertically by half of their height, and then subtract the top. Right, so move half of them upwards and the other half downwards. Subtract one set from the X ribs and the other set from the Y ribs. So as you can see here, we're moving one upwards, the other downwards. We're actually scaling them, but it has the same effect. And then we're going to subtract those from the original ribs. So that looks like this. And we're also going to scale the ribs, make them a little bit thinner. This just helps with the Boolean operation and ensures that it works well. So that's the way that we create the notches. From there, it's a relatively simple step to just resection the newly notched curves. So you can see here the basically the original section lines, but with notches. And finally, we can also scale the ribs to get the actual waffle frame as it will be built. So this is an actual digital representation of the physical object. And finally, we're going to use a curve layout tool, which I will be providing. It's a component in a cluster that I've developed that basically uses an algorithm to lay out curves in the most efficient manner. So I'll be providing that. Okay, well, let's get started here. Now, let's see. So this is our definition, but we're going to go ahead and create a new definition. So let's see this quickly. Let's all go in and create a new definition. And if this is the future, which it likely is, we are using Grasshopper version 0.9.0014. So if things seem to be a little bit different in your component tabs, just look around, see what you can find, and do your best. Okay, so let's get started. So I've already created this object here, and I'd like you all to follow along. This is just a three-dimensional object. It has some double curvature. It's a little bit interesting. It might be some sort of a basis for a canopy or something, or just some sort of spatial exploration. But I'm just going to use this. If you don't have this, you can just draw a very simple object. I mean, it could be just a couple boxes, anything like that. Just something fairly simple. And then maybe just Boolean these together, and there you go. Okay, so that's a possible object. Anything works. I'm going to use a little bit more complex object, just because it helps to show what the definition is actually doing. Okay, well, so the first step is, of course, to bring in our parameter, which our object in this case is going to be whatever object you've created. So we're going to bring in a brep component under geometry, and we will set one brep and select our object. At this point, I'm just going to go ahead and hide that object in Rhino so that it doesn't get in the way of what we're doing. We'll be able to see everything a lot better. Okay. So the first step, as we set up, was to find that grid underneath. And so the best way to do that is to first find the bounding box of the original object. And the reason we are doing it that way, rather than just creating a grid, is that this locates the lines perfectly under the object, and no matter where the object is in the Rhino field. So if it's if it's a building component and you don't want to move it out, you can just use this as a definition, it'll do it on the location. Okay, so let's jump in. Here we go. All right, so under surface, we'll go grab a bounding box, and we'll bring that in from Brep to C for content. Okay, so here's our object. Here's our bounding box. And now what we would like to do is to find the bottom 4 corners of that bounding box. And we're going to draw lines to create the 4 lines that are going to be the basis for our grid. So bounding box, you're going to box corners, you're going to find under surface analysis, and it's this little guy right here called box corners. Just connect that into the first B, although it actually doesn't matter then. Should both work in this case. Okay, so then we're going to create a series of lines. So under curve, we'll get this line component, or line 2 point. Okay, so follow along here. We're gonna we need to make 4 of these because there are going to be 4 lines along each of the bottom edges. Let's go back here and just turn off this bounding box. As I go along, I'm going to turn off a lot of the objects. Try to just keep up. It'll keep your workspace a lot less cluttered. Okay, so we need 4 lines, so let's make 4 copies of this. Okay, and we'll just drag those down, give them a little bit of space. Okay, and so the first one, we're going to go from A to A and B to B. That's pretty straightforward. Okay, the second one is going to go from D to A and from C to D. And that's going to give us a curve going in the same direction as that first curve from A to B, because the points are actually going 0, 1, 2, 3. So we want to actually go from 3 to 2 and 0 to 1. So that's this ordering over here. Okay, so then we need to get the other 2. So that's going to be from A to A and from D to B. Okay, and then the last one is going to be B to A and C to B. Okay, so now we've got our 4 curves right along here, looking good. So now that we have those, we want to divide our those curves to get points from which we're going to create lines and extrude those lines to create the intersection planes. Okay, so we need to divide curve, so that's going to be under curve division, divide curve. And again, we're going to need 4 of these, so let's just make 4 copies. Okay, so then we're just going to bring one of each of the lines into the divide curve components, and from there we now need to decide how many segments we'd like to have. So right now there are 10 segments and 11 points, actually 9. There would be 9 intersection planes. But we want to be able to control that, and that is going to be our parameter, our variable, the number of frames in the x direction and the number of frames in the y direction. So for this, of course, we're going to go to the slider, and let's just excuse me, set this. We're going to go to integers, and let's do 0 to 20, and we'll make a copy of it, and we're going to rename that the first one will be number of ribs X, and second one will be number of ribs Y. Okay, so let's just look really quickly. These, as you can see, if you click on the lines, you can see this is our y-axis and this is our x-axis. The first two are running parallel to the x-axis, so the ribs are going to be running in the x direction. So I'm sorry, in the y direction, but it's the number of ribs in the x direction. So that's actually going to go from number of ribs x into n. And you'll see they'll all disappear, but then if you come over here and type in 4, you'll get 3 division points, or 5 division points, but 3 3 points that will eventually turn into planes. So 3 planes. Okay, let's connect the other set down at the bottom here. And we'll increase that to 5. Spacing looks good. So those are our variables. And in fact, we only have one more variable. We might as well create it now. Let's do it. Okay, so this is going to be called rib thickness, and that was T. And we'll just leave that at 0 to 1 for now. That's probably about where you want it. Okay, so moving forward, so now we need to create some lines that go across to create that bottom grid. So that's not too hard. We'll just create a series of lines between 2 points. So again, going back to line, 2 points. And here we actually only need 2, so we'll just make a second one. And now if I connect the points out of divide curve into that line, you can see now we've got our lines across here. We've got 5 lines, 3 that will actually turn into planes. And as we go down here, we'll get 4 lines that will turn into planes, total of 6 lines. Okay, so from then, what we are hoping to do is to get rid of these outside lines. So let's go back just quickly. We'll turn off the box corners. Just keep hiding stuff here, and let's turn off the curve divisions and the original lines. Okay, so now we've just got our 2 sets of lines here. And so what we'd like to do is to eliminate these outer lines. So there's a few different ways to do this, but my favorite trick is to create a series of numbers starting with 1 and ending with the number that you would like to have, and use that as a series and use that as an input into list item, and that'll basically eliminate the first and last entries. If that doesn't make a lot of sense, just follow along. I think it'll make more sense once you see it done here. So, okay, so we're gonna go and grab a list item, and we're gonna make a copy of that. And so the list item is going to the list that we're going to be taking items from is are those lines. Okay, but now we need to make a series of numbers that are going to start at 1 and end at 1 less than the last number. So and the output of that series is going to be our integer. So we'll just go ahead and click those into integer. So right now the first number is 0, and the step size is 1, and the number of values is 10. So the first number we actually want to set to be 1. So let's go ahead and do that for both of them. Okay, so now we need to figure out however many lines there are here. We want to have, we're essentially, we're getting rid of one in the beginning and one in the end. So however many lines there are, we're getting rid of 2 of them. So we need to figure out how many lines there are and subtract 2. So what we're going to do, I'm just going to make a little bit of space here. We're going to get the length of the list. So that's under sets and list length. So that's going to give us basically the number of lines that there are in that list. Let's make a copy and bring it down to the other set here. Okay, so we're looking at 2 numbers, 6 and 5. So what we want is to have 3 and 6, irrespectively. So let's just go to Maths, and we'll use the expression editor. Just a kind of convenient way to do it. Get rid of the y and double-click to edit, and we're just going to do x minus 2. Okay, so that'll give us whatever the input is minus 2. So right now that's 5 for this one. We want to have 3 curves, and you can check it by saying, okay, you want to get rid of this one and keep 1, 2, 3, so it looks like it's working. Okay, so we want to have 3. We've got 3. Looks like it's going to do the right thing there. Drag down a copy and hook it into the other list. And now if we put that into C for count on series, you'll see that it'll give you, out of the series, you'll get the numbers 1, 2, and 3 for the first set, and 1, 2, 3, and 4 for the second set. And if we go back quickly and change this, you'll see that in fact it'll adjust automatically. So if that's 7, now we come back over here. The integers that are going into list item are 1 through 6. So, and the number of items in that list is originally 8. So it's 8 minus 2 equals 6. And we get those 6 values. And now if I were to select this, and I'm going to go back and hide those lines to emphasize the point here. But now if I select these list items, you'll see they have actually gotten rid of those outer curves. So that's looking pretty good. So it looks like we're in good shape. Okay, so now we need to extrude the curves upwards, right, to create that sort of 3-dimensional intersection set of planes. So to do that, we're going to go to Surface and grab Extrude. Okay, now the base profile for the extrusion is going to be those curves. So let's drag those into B. Now the D direction, which is really a vector, we need to establish that vector. So I'm just going to move this down because we're going to be referencing something from earlier in the definition. Okay. So to get that vector, we want to make sure that it goes all the way to the very top of the bounding box of this object, right? So if we go back here and we look at this bounding box again, if it doesn't go all the way to the top, then we could run into trouble if there was a rib that was here. It'll get cut off at the top. So we want that height, so we're going to extract a line from the edge of this bounding box. And so the way that we do that is we're gonna essentially extract a line. We're gonna actually do a little bit of a shortcut there, but it's essentially the same idea. So I'm just gonna move this down here, and what we're gonna do is we're gonna use a very nice tool in here called Evaluate Box. Box Components. And we'll hook that into B for box. And what this does is gives you the dimensions of the box in the X, the Y, and the Z directions. So so those values are going to become our, and so we're actually only looking for the z value. Those z values are going to become our vectors. Sort of like one kind of fancy little fix in Grasshopper, if I hook this z domain from this box into a vector, it'll actually just give me a vector with the with an amplitude of the span of the domain. So that's pretty convenient. We'll just go ahead and use that. Okay, so let's drag this guy over. Okay, and we'll just hook that right into D on both of those. Okay, so now let's go back and turn off this box, and we'll turn off the evaluate box, and we are looking pretty good. There we go. Okay, so we've got our vertical planes. They go all the way to the top of the object, and the intersection looks like it's going to work. Okay, let's turn off these list items, which are the original lines of the grid, and those have been extruded, and we're not going to need them anymore. Okay, we are cruising right along. Okay, so now this next part is essentially finding the waffle, and the way that that's going to work is by using a it's called a Brett plane intersection, so it's under intersect, but it's essentially a section. So it's under it's under physical, and it's going to be no, it's not. It's under mathematical. It's a Brett plane, and it says otherwise known as a section, and when you lay it out, it actually is called SEC for section. Okay, so we need to create two of these, and so let's make a copy. And so the original Brett that we're going to be sectioning is actually our original object. So we'll just send this guy, send this guy all the way back to the Brett, and drag another one in. Okay, and the planes are, of course, our planes that we've created, those vertical surfaces, which, again, through some wonderful fluke and Grasshopper, are both planes and surfaces. So that's kind of a nice dual identity. Okay, if we turn off the preview on these extruded planes, we can now see that we've got our section curves. If we turn off the original Brep here, we're also going to get a chance to really see what's going on here, and it's looking pretty good. We've essentially got our curves. If you were to lay these out, you could cut out the notches manually and achieve the same result. But of course, if you're going to cut them out on a laser cutter, you might as well create the notches. So that is really the gist of the definition, is trying to create those notches. This first part is fairly simple, but the next part is going to be a little bit more complicated. We're going to do our best here to make it as simple as possible. Okay, so well, quickly we're going to just turn those curves into surfaces. So under surface and under freeform, you'll find this planar surface component. Make a copy of that, and there we go. So let's hide these sections. Actually, we won't be needing those anymore. We're just kind of moving forward with this definition. Okay, so there are our surfaces, and from here, what we would like to do is extrude those 1/2 of the thickness of the actual material that we're going to be cutting. However, if you just extrude it from where it is, extrude it in the X direction and the Y direction, you're going to end up with a waffle that's essentially the notches are not going to be in quite the right place given the intersection. It's going to be offset by 1/2 of the thickness of the material. So instead what we're going to do is we're going to move the objects over by half of the thickness of the material and extrude them back by the full thickness. And that'll give us a solid object that's going to be centered on the original planar surfaces here, but it's going to have the correct thickness. So to do that, we're going to need a couple commands. First, we're going to want to pull out a move command, and it's going to be 1 for each. And then we're going to bring out an extrude command. Okay, so that'll be under surface and extrude. Make a copy of that. Okay. So we are going to be moving the surfaces, so that's going to go into geometry, G on move. So we'll hook that in. So then, and then that geometry is what we're going to extrude. So let's hook those into extrude. Just sort of set up our framework here and then fill in the pieces. Okay, so these planar surfaces are running in the Y direction, but they're spaced in the X direction. So we're going to go ahead and move those in the X direction by 1/2 of our desired rib thickness. So if we go to vector, we'll bring out an unit X vector, and then for the others, they're of course going in the other direction, so that'll be a unit Y vector. So let's just hook those right into move. So as you can see, it's already offsetting them, and it's moving them a unit of 1 to in the X and the Y direction. But we don't want it to move 1. We want it to move 1/2 of our thickness. So if we go back over here, we have conveniently already created this rib thickness slider. And if you haven't, now's a good time. Okay, and let's just give ourselves a little more space in here. Okay, so this this number is going to be the amount that we extrude the surfaces once we got it there, but first we need to move it by 1/2 of this thickness. So to do that, we're going to divide by 2. So let's go ahead and use expression editor for that. Go in, get rid of that Y component, that Y variable. And so it's going to be X divided by 2. Okay, and so then we'll hook in our rib thickness into X over 2. And so now we've got a value of 0.25 and the resulting value of 0.125. Okay, so we want to extrude we want to move the surfaces a value of 0.125 in the X direction, and then we'll make a copy down here and move those in the Y direction. Okay, so now we've sort of achieved 1/2 of our desired goal, right? We've moved it from here to here and from here to here, but now we need to extrude it back over to the other side. And so that extrusion is going to happen in the negative X and negative Y directions, and it's going to have a magnitude of the actual rib thickness. Okay, so let's create a vector, and so we will to do that we're going to use amplitude, and we're just going to borrow our unit vector, or our X vectors and our Y vector from the other one. Since we're going to be changing the amplitude, it actually doesn't matter. And so that amplitude is actually going to be the thickness of the ribs, like we said. So right now, let's just go ahead and hook this one in, and you'll see. Now it's extruding it. So first it went, this is the original one, and then it moved to the middle here, and then it extruded even further to the right in this case, but further down the x-axis. We actually want it to go in the opposite direction. So to do that, you need to reverse the vector. So that's going to be under vector, reverse. So let's hook that into amplitude and D for direction. And it looks like it's working. Okay, so we had our original planar surfaces, then we moved them in the x direction, which you can't really see because of the angle, but it's this outer side here, and then extruded it back, the full thickness of the rib. So that looks like it's working. Let's just make a copy of that reverse vector down to here for the y direction, and hook that into extrude. And it looks like everything has worked out quite well. Okay, let's go ahead and hide these old surfaces, and we're just going to move forward with the solid objects. Okay, and if you guys felt like it, you could certainly rename these. You know, extrusion, solids, X, and extrusion, solids, Y. Okay, that'll just help you to sort of know what those elements are. I'm just going to go ahead and group them so we know where we're at. Okay, so actually we're getting pretty close to where we're going to stop for today. But right now we've got our we've essentially got our waffle. This is the finished solid waffle minus the notches. So what we're going to do next is find these intersection events here, and we're going to do a couple extra steps, but essentially we're going to subtract those intersections from these original frames, and we're going to use those intersections. We're gonna move them upwards and downwards and use those intersections to create the notches. Okay, so I'm just gonna take it a couple steps further here, and then we're gonna quit for the day. But so if we go to intersect, over here you are going to be looking for BREP intersection, which is intersect physical BREP. Boundary representation. Okay, so and finally, these sort of two parallel strands of our definition are going to come back together. Now, if we just go ahead and hook these in, you'll see that because of the way that the data trees are organized, it's going to reference sort of the first one in the y direction to the first one in the x direction, second to the second. So here and here, third to the third, here, and fourth to the fourth. And then it's going to reference the fifth to the fourth and sixth to the fourth. So that's not actually working. What we would like to do is reference each of the ribs to each of the ribs that intersects it. So essentially take this rib and say, okay, there are 1, 2, 3, 4, 5 intersection events there. 6 intersection events there. So the way that we're going to do that is by flattening one of the data trees here, and we are going to choose the one going into A, and I was going to do it in the component background just to make it clear so that everybody sort of knows what we're doing. If we go to sets, you're going to find over under tree here, you'll find flatten tree. So just stick that in, and the data that we're going to flatten are these extruded solids. And then we're going to go straight into BBX, the BREP intersection. And now you can see if I select that object, we actually get all of the intersection events that we're looking for. And if we zoom in, you can see that they're curves. If you zoom in further, you can see that the curves, that it's actually, in most cases, not always, but in most cases, it's 2 curves for each intersection event. Then that's just sort of the nature of the beast. Basically, the points where they intersect are directly in the center of these top kind of cross lines here. So you can, I mean, you could certainly do some fancy math, but we're just going to go ahead and do something pretty simple and take the bounding box of these curves. And those are going to be our French fries. And that seems to be a better way of doing it. You certainly can use a solid intersection, which would be under intersect, and over here, solid intersection. But I've found that actually it's a little bit buggy, and this seems to work really well. The Boolean commands in Grasshopper are just a little fussy, and you can certainly use them, and in fact we have to use it at a later step. There could be a way to avoid it, but it seems to make sense to use it. So this seems to be a much better way to do it. And you want it to be set, right now it's set per object, so what I was saying, how each of these is sort of a small box, you can, a set of 2 lines, you can see that now those lines are each getting their own individual box, but that's not what we want. What we actually want is for each of these sets of lines to have its own box. So if you right click on bounding box, you have this choice for union box. That's Woody Guthrie's box. So if you zoom out, you'll see that now it seems to be working a lot better. This seems to work well as a method for finding these French fries. You certainly could try to figure out sort of a different version, but this one seems to work well. If we go ahead and hide these 2 things, we'll clean up our Rhino field a little bit. Okay, so we've got our Y direction ribs here. Our X direction ribs. We've got our Y direction ribs, and then we've got the intersection events. So in class on Tuesday, we're going to be going over how to subtract those French fries from these breps here, from the ribs, and we're going to use that to we're going to subtract those, and then we're going to use the section tool again to find the new sort of section lines from our original planes and those sort of new notched pieces. And we're going to reorient those onto the XY plane using the component which I will be providing. Okay, this has been the first part of a Waffle definition for the UMass Amherst Analysis and Representation 2 class in the spring of 2013. Good luck, guys, and we'll see you on Tuesday. Take care.